the lecture series where we are at present discussing some kind of hybrid systems, where we are looking into how can we use the neural networks, how can we use the fuzzy logic, how can we use the evolutionary computing, all these along with some kind of heuristics. And what we do is that we try to gain in something what the individual systems did not have. We gain something over these systems, and when we gain something over these systems, we are able to come up with systems that are really good. We are able to come up with systems, those systems that perform very well. So now we'll have a look. We'll of course exceed the same thing. We'll have a look into yet another hybrid systems, and that hybrid system is a hybrid of neural network along with fuzzy inference systems, what are known as the Neuro Fuzzy system. They have elements of neural network and fuzzy system, and what we would be calling them is the adaptive Neuro Fuzzy Inference System. So there's some neural part to it and there's some fuzzy part to the name. There's a component that comes from the neural network, and there's another component that comes up from the domain of fuzzy inference systems. Now, whenever we are working with fuzzy Neuro Fuzzy system, it's important to realize what do we take away. What is the taken that we get from the individual systems? What are the components that will be taken from the neural network? Those would be the good parts of it. And what will we be taken from the fuzzy inference system? Those would be the very good part of it. Now coming up towards the second part, that is the fuzzy inference systems. Now we've seen multiple times where the kind of problem with these systems was that I need to keep on modeling the various membership function, modeling the various rules, doing all those kinds of things. Of course, in evolutionary computing, we added the pattern that an evolutionary computing does that, but to a large, there was some human who was trying to create some kind of rule system, anything. So there is some kind of limitations of the fuzzy inference system. And if there is limitation, there will be something very good to it. The good part is very good modeling that these systems have. What is good in these systems is that I can model up any of the real life applications, because most of the applications, the way they behave, we see that there is a fuzzy behavior in them, and that's why the fuzzy inference system becomes very good to all these systems. They are run by a set of rules that we write, so that's again a good part of it. The system is completely understandable. It's not like your system will give it any vague output. You can always study, you can always understand what the output is as a result of the rules that the system has. And of course you can modify the rules if you are to make your own system for it. You can always modify the rules. So there are some very good takeaways that we get from the fuzzy inference system, but the limitation is that in its pure format, there is a lot of problems that a person has to formulate the entire system. We come to the second part of it, that is the neural network part of it. The neural networks are again very good systems. What the neural networks essentially do is that you give it a database, it will learn it for you. Very high generalizing capability. So you need not specify anything, and that's why we sometimes say that the neural network is a complete black boxes. You feed it anything, you get out the complete system. You feed it anything, you get out the complete system. You may or may not understand what goes inside that black box. You may not understand any part of it. So highly good, very fair learning capability is what these systems have. A very high degree of learning capability is what these systems have. So the big question is that can we borrow the very exciting problem modeling, the very exciting rule-based behavior from the fuzzy system, and very good learning capability from the neural networks, and we can make it a hybrid of the fuzzy inference systems as well as the neural network system. If we are able to do that, we'll get in a very good functionality into our system. If we are able to do in something like this, there would be a very good functionality that we get out of the entire system. Those would be very exciting fuzzy systems that would be able to really learn up well. So you give them database to these fuzzy systems and then they do some kind of learning. They do some kind of learning and they come up with their optimal formats. So you need now you need to only work with fuzzy system as if you are working out with a neural network. You can be as careless as that. You can be as it can be the same ease that we have in neural network we now have in fuzzy system, only because we are trying to add in the learning capabilities outside the neural network and into a fuzzy system. So how is it that I am able to do that? And for that we study what is the architecture of ANFIS, or of an adaptive Neuro Fuzzy Inference System. What does the architecture, what exactly the architecture of these systems is? So we come over the architecture. Now I can interpret the architecture of ANFIS in two ways. I can always assume that the architecture can be interpreted in two ways. It can be seen in two ways. One of the view of this very architecture would be as if it's entirely a neural network. It will contain some multi-layers perceptron, it will contain some neural arranged in multiple layers. So one of the views is that it would be entirely a neural network, and the second view would be that it is completely a fuzzy inference system. So in what I draw as the architecture of ANFIS, you will get two beautiful views of it. One of it says that it's a neural network and the other says that it's a fuzzy inference system. So why do I make the architecture like that? I know that the ultimate aim, the main aim that I have in these systems is that I have to borrow learning capability from the neural network and put it into fuzzy inference system. And for that, what do I do? If I can superimpose a fuzzy inference system over a neural layer architecture, if I superimpose a fuzzy inference system over a neural layer architecture, I will be able to use the same learning mechanism as I do in my neural network. If I am able to get this superimposition done, if by chance I can have the superimposition done, then my fuzzy inference system will behave exactly in a similar way as my network does. My fuzzy inference system will be able to learn using the same training procedures as we had into the neural network. So we write down the architecture first from the point of view of a neural network. That is how we write down the architecture. So there will be an input layer, there will be an output layer, and there would be multiple hidden layers in between. That's what multi-layer perceptron says. And we follow the same principle. So there is an input layer. Let me say I1, I2. The number of inputs to the system is equal to the number of neurons that this network has. So this is what is the input layer. There is a hidden layer. If we talk about the fuzzy ANFIS, it's a 5-layered neural network. The ANFIS is a 5-layered neural network. So this is what is the first hidden layer. This is of course the input layer, which is a passive layer, and sometimes call it as layer 0. This is passive in nature. This is the next layer is known as a membership function layer, for reasons we'll discuss later, but this is what layer 1 is. This is what layer 1 is. So I'll have multiple connections like this. So from this we move up to the next layer. into our very own system, we move on into what the next layer is, which is known as a rule layer, which is of course your layer 2. The next layer is known by the name of a rule layer, for again reason we shall see later. But this is what layer 1 is, this is what layer 2 is, and what I am doing is that I am just trying to draw in a simple multi-layer perceptron of 5 layers. So there is a layer 3 over here. There is also a layer 3 over here. This layer is known as the norm layer. So the next layer is known as the norm layer. So like this, I will have my norm layer over multiple architectures like this. I still go further. The next layer is known as the output layer or the out layer. This is the layer 4. I have one out layer, and towards the end, of course, I have my final output layer. This is what is layer 5. So that is what becomes my layer 5. So in all, it's a 5-layer neural network. The input layer, which is layer 0 or the passive layer, the membership function layer, which is layer 1, again consisting of multiple neurons. Again, there is a layer 2, that is the rule layer, again consisting of multiple neurons. The norm layer followed by the out layers and followed by the output layer. So it's very much a specially grown multi-layer perceptron of limited connectivity, not all connected architecture. It's a simple it's a 5-layered multi-layer perceptron of limited connectivity, and limited connectivity is something that we have seen, we have done, we've experimented, and it works. So the neural network architecture is quite clear. Each one of these neurons would be a normal neuron, and a normal neuron is just a processing element. It's just something that does some kind of processing. And we'll see into how the processing is similar to the processing done by any of the neuron of a multi-layer perceptron that we saw. So that is what is the view of this system as a artificial neural network. This is what is exactly the view of this system as a multi-layer perceptron. So my task, the second task that is left is if I can show that this is also the view of a fuzzy inference system. If I can show that this is also the view of a fuzzy inference system that has the same functionality as any of your conventional fuzzy inference system would have. If I can show this fact, my first task is over, and my first task was superimposition of a fuzzy system over a neural network architecture. So the point is that how is it equal to a how is it equivalent to a fuzzy inference system, and how does it perform the same task? And that is where we delve into the working of this architecture. So like any system, the number of inputs is equal to the number of input neurons, and the number of output, that is only one in this case, is equivalent to the number of outputs. Remember when I did problem solving using fuzzy inference system, it was a very simple stage of task that I performed. It was a very simple stage of task that I used to perform. Again repeating those tasks, I used to say that I'll take in each and every input, and what I'll do is that I'll write down the membership functions. I'll take in each and every input and I'll write down what the membership functions are. So each input would be divided into a set of membership function. The second stage used to be that I'll see how these input and various membership functions, with what combination are they interacting with each other. That is what I call them as the rules. That is what I call them as the rules. how the various membership functions interact, how which membership function of the input interacts with the other membership function of the another input to form some kind of output. That is what I wrote down as a list of rules. The rules had two parts, the antecedent part and the consequent part. Every rule had two parts. One was the antecedent part and the other was consequent part. I handled both of them separately. I used to first work over the antecedent part. Then I used to apply some kind of implication operator. And then I used to migrate towards the output part. That is how I solved one rule. In parallel, I used to solve all these rules and integrate their outputs. That was the aggregation operator. So after I worked with the antecedent and the consequence, I used to integrate their outputs. That was the aggregation operator, which was of course followed by the defuzzification operator to get the final result. What you see here is more or less the same system. More or less the same system, we just need to get a motivation that it performs in a similar manner. So let us go layer by layer, see which part of this network, of course now it's an artificial neural network, so let us see which part of the neural network does what processing of the fuzzy inference system that we have tried to superimpose. So the input is again a passive layer, so there is nothing to do with this input layer that we have. The second layer is known as a membership function layer. What the input layer does is that it simply gives its input to the membership function layer, and the membership function layer, like in the first layer of the neural network, does some processing. I used to divide the inputs into some membership function, something like low, medium, high, slightly bad, medium bad and whatever. I used to divide all the inputs into some kind of membership functions, and that is exactly what I am doing here. This input is divided into 3 membership functions, this input is divided again into 3 membership functions. So what's doing? This neuron has only one input. This neuron has only one input. When I divided the inputs into multiple membership functions, what I said that the membership function of the input I1 and the membership function low would be given by some fx, let's say 1 plus e raised to power minus ax. I used to work in this manner when I used to solve problems using the fuzzy inference system, and this I repeated for all the inputs and all the membership functions. These are exactly the same equations that I wrote down at the time of discussion over the fuzzy inference systems. These are exactly the same equations that I wrote down at the time of the fuzzy inference systems, working with fuzzy inference system. I only say that here this term membership function in an artificial neural network is changed by the activation function. So what happens, because it is a single input neuron, this one, this one, this one, this one, or any neuron of this layer, because it is just a single input neuron, because it takes only one input, this neuron takes in only one input. So what happens is that submission WIXI, which was my first step in case of working with an artificial neuron, this submission WIXI for I equals to 1 to n converts into some W and some X. If the weight is kept unity, it becomes the input itself. And that is what exactly this thing is doing. Because my submission WIXI would be no longer active now. It would be simply a unit function which will not do anything. So after the submission unit, which is not the case to be applied over here, the second part is the activation function. Every submission WIXI was passed over some activation to provide some kind of non-linearity if it ever needed to be included in the system, it was to apply the input over some kind of activation function. So what do I say is that if this is the equation of the activation function, which is nothing but my membership function, if this is the equation of the activation function, the output that this neuron gives, the kind of output that this neuron gives is going to be exactly mu for the input I1, the membership function low, mu for the input I2, the membership function medium, it's I1, and so on. So all the outputs of this layer, they do only one thing. All the outputs of the neurons of this layer, they give you what the membership degrees are. They give you what is the kind of membership degree of any input. And again, remember, if I give you any homework that you have to solve a fuzzy inference system, the first thing that you always do is to find out the membership value for all the inputs for all the membership functions. That is precisely the first task that I've done. Whenever any input is applied, the first thing I've done is that I've tried to find out what is the membership degree for all the inputs for all the membership function. So if the first task is done, how do I proceed with my fuzzy inference system in this neural network architecture? We know that the next step is always a very simple step, that is formulation of the rules, that is working out with the rules. So what do I see? And the antecedent part of it. That always whenever we worked up, we took the antecedent part first and we worked over with the antecedent part of it. So the next step we'll do is to work over with the antecedent part of the rule. Antecedent part of any rule is of the form if input 1 is low and input 2 is medium and something. So this was what was the antecedent part of the rule. This is exactly what was the antecedent part of the rule. So we work over the antecedent part. Now, whenever I worked up again with these kinds of rules, I change them over the membership values. I change all of these over the membership values. So there will be multiple of them. I replace all of them with the membership value and apply this AND operator. I used to convert all these into some kind of membership values. And after the replacement with the membership values, after the replacement with the membership degrees, I used to perform all these AND operators. It is again known what AND operator was nothing but a minimum or a prod. The AND operator was nothing but a minimum or a prod depending upon how you model the system. But after all this, I used to apply these AND operators, and after that what I used to say is that the complete equation, the antecedent part of it, will get replaced by a membership degree. I used to say that the complete antecedent part of it will get replaced by a membership degree. How I use this membership degree is something, of course, that lies in the consequent part of it, that is by the application of the implication operator. So we are not going that far, we are only dealing with the rules. So that is what used to happen in case of a fuzzy inference system. Can I do exactly the same thing out over here? Can I do exactly the same thing out over here? So what do I say? Let every neuron of this rule layer represent a rule. So if my system has m rules, there would be m neurons over here. If my system has m number of rules, this is what these neurons would be. If my system has m number of rules, there would be exactly m number of neurons over here, with every neuron here, with each and every neuron over here denoting one rule that the system has. Each and every neuron over here will stand for one rule. So these are parallel processing units, so as in fuzzy system, all the rules will work parallel in nature. that's again an analogy between the neural networks and the fuzzy inference system, all the neurons will work out to be in parallel to each other over here. So I solve the system for one rule, the others will be following exactly the same scenario. So I say, let me solve this rule, R1. Now I say the rule R1 is if input 1 is low and input 2 is low and input, let's say N is medium, then something. I formulate this rule like this: if input 1 is low, input 2 is low, input N is medium, I know I will be replacing this rule by something like mu for the input 1 membership function L, mu for the input function, for membership function low, input 2, and something, and it goes till input N. So mu for input N for the membership function medium. This is what would eventually happen out. This is what would happen out. So I need to give the system mu I1L, mu I2L, and so on till mu I2N. I give this input mu I1L from here, mu I2L from here, and mu INN from here. This is what the system that it gets. So there is no other connection. The only connections are that the membership degrees that this rule is using. Now again, every rule basically works for the membership degrees. So I have given as input the exact membership degrees that this rule uses. So what it does is that the first part, it needs to do some kind of summation. The first part that it needs to do, this new artificial neuron needs to do it some kind of summation. I say in place of summation Wixi, I use the equation pi. Wixi, let me say that all the weights are unity, it becomes pi xi. That is what is the summation part of this neuron. It's natural it always have a summation part and activation function. So I need to model both for this neuron. I say that the summation part will be given by a pi. In place of sigma, it will be given by a pi. So basically, when all these input comes, I basically take the product. I replace the summation by a pi. So whenever these inputs come, I simply take the product in place of taking in a sum. So again, the task is very simple. I have taken the product. What I have done is that I have, in doing that, from the neural point, from in the neural network, in doing this in the neural network, I have implemented the AND binary logical operator. I have implemented out the AND binary operator, the AND fuzzy operator, as soon as I change sigma to pi over here. So the AND is already applied. The AND is already applied. So what the activation function of this neuron is, it is nothing but pi, all the mu that it's getting. So it's mu for any input I and the corresponding mu j, I equals to 1 to n. That is what it's doing. It's adding up all the, whatever connections are there, it's adding up all the, it's doing a pi, and that is what I get as my output of the antecedent part. So let me say that my output of the antecedent part now is what is, I'll have to take a variable over here. So let me say that the output is simply O1, and that is what O1 is equal to. Now again, remember, I am not applying any kind of activation function over it, or you can say that the activation function was simply linear, fx equals to x. I do not need any activation over here as per my fuzzy inference system methodology. In this system, I do not need any kind of activation function, exactly because my fuzzy inference system does not require any kind of non-linearity or anything. It's an AND implementation simply pi. The AND implication is what is simply a multiplication, it's simply a pi. I move in exactly further out from here into what the next neuron is. So what does the next neuron do? Now over here I will just need one check. While working out with this fuzzy inference system, I will just need the check that the activations are always normalized. Whatever output I produce here, they always need to be normalized. When I say that they need to be normalized, I say they should be between 0 to 1 with the sum as 1. So the actual membership values, the actual membership degrees that I will be working with, when added for all these outputs over here, it should produce me 1, and each one of them should lie between 0 and 1. So what do I say? O2 out over here. This is for any neuron. Let's say that the output is O1. For any neuron 1 here, it is O2, O1. For any neuron 2 over here, and this is OM. This is O1 for any neuron M over here. So the first one gave me output of O1, 1. The second neuron gave me an output of O1, 2. The third rule gave me an output of O1, 3. The nth rule, that is last rule in my system, or equivalently I can say that the last neuron in the system, it will give me an output of O1n. So all that I need to do out here is a task of normalization before I work further in this architecture. Before I work with this architecture, I'll have to carry out normalization as per the problem specific, as per the modeling requirements. So I simply say that I carry out OJ So what would be the output O2 for this neuron 1? What would be the output O2 for this neuron 2? What will be the output O2 for this neuron N? That is what I need to find out. So for any O2, for any output of this neuron simply carries forward a normalization task. So that's a very simple task that it carries out. So O2, the output O2 for the neuron J is nothing but a normalization. So I say that it is simply O1 for the neuron J divided by summation of O1 for the neuron J. It's as simple as that. After that, I'll get all the normalized values whose sum would be 1. So if I do summation of O2J for all J, so dividing from 1 to M, I simply get 1 as my output. And again, what can be said is that this task can be easily modeled in a neural network, where a summation of the previous outputs would happen. So if all these outputs are going, there would be a summation part of it, and there is an activation function that reciprocates it, and whatever is the immediate output, it multiplies it with that. So you can, of course, using the activation function part of it and the summation part of it, you can use this kind of architecture. You can use the same neural network architecture. A neuron ultimately needs to do some kind of basic processing, and that is what it's doing. So I play around with the activation function of this neuron, or the norm layer neuron that performs normalization task to get my output over here. So these are again outputs. These are again membership degrees. These are again membership degrees, but normalized membership degree, and that is how I will proceed out with my example output over here. That is exactly how I will proceed in dealing with this problem. So once I've got my outputs ready, once I've got my membership degrees ready of the antecedent part of it, next I would like to apply some kind of implication operator as per my fuzzy modeling. The next thing that I might like to do in modeling a neural network, modeling a fuzzy inference system over neural layer architecture, the next thing that needs to be done in this fuzzy inference system is that I do some kind of implication operation. Now remember, if condition antecedents, implication y equals to a1 I1 plus a2 I2 plus a3 I3 plus so on plus an In. I'm unfortunately not sure whether it's the Sugeno or the Mamdani system was probably a Mamdani one, in which outputs were modeled like this. So that's how we've already seen that a rule may not be if input 1 belongs to some membership function, input 2 belongs to some membership function, then output belongs to some membership function. It can always be in the form of a linear addition of the inputs. And that's why we never applied membership function for the outputs. We always did that only for the inputs, never for the outputs, because we did not need it. So again, I'm unfortunately not sure whether it's Sugeno or it's Mamdani, but that is what the modeling scenario is, that the output is always linear addition of the inputs. And what this implication operator does in this case, that we have already seen that if m is the firing degree of this antecedent, if antecedents have a firing degree of m, my output will be m into a1 I1 plus a2 I2 plus so on. So it will deplete, it will degrade the output to a degree of n. That is what it was supposed to do, that is what it does. It degrades the output by an amount of n. That is what we've already seen what the fuzzy inference system works. That was what was a basic working methodology of a fuzzy inference system, where the implication operator simply takes a product. It simply takes a product of the membership degree along with the linear output over here. It always takes in the membership of degree and the linear output over here. So again, this is what this neuron is supposed to do, the out neuron. The out neuron, this was the membership function neuron, this was the rule neuron, this was the norm neuron, this is the out neuron. Out neuron carries the task of implication, that is mapping of the inputs to the outputs. So that is what it does, is that it carries forward the application of, it carries forward the mapping of inputs to outputs. So this neuron architecture, I'll draw it a bit separate. I'll draw the output separate. So if this is any output OJ, if this is any neuron of this layer, the neuron J of this layer, it is given all the inputs as well. So it has all I1 set to In, and these are weights A1, A2 to An. This is what the architecture lies in. It is given a copy of all the inputs along with their weights. And that is what we already know, and plus it is given out, it's of course given out the bias B, because we know that we always had the equation of the format of summation AI W AI input I plus a bias term that is always added in the fuzzy inference system, that may be added to control the output. So we'll give it a bias like this over here, we'll give it a membership degree curve over here. What it will do is that it will perform a summation part. It will perform a summation first of all. Bias has a weight of 1. So this will become summation of I varying from 1 to n plus B. That is what it does with these inputs. With these inputs that this neuron had, this is what it does, and the activation function I apply is a product. It takes a product with m. So again, I have modeled this using the a slightly unconventional manner, where I was differentiating between the inputs. The input m was handled separately, as it was the case with this equation. But what ultimately happens is that this neuron, it takes the summation of all the inputs, of course a weighted summation, along with the bias term, and it multiplies it with the input known as the firing degree of the rule. And that is exactly what this is exactly what was happening in case of a conventional fuzzy inference system. This is exactly the case that was happening out over there. So I got this out. Let me say output of this neuron is O3. This is O31. This is O32. This is O3. This is O3M, where there are M nodes to the system. What has not been drawn is that they are of course additional input. A copy of this input comes up like this out over here. If this connection has some weight out here. So all these connections, they actually exist. These are the connections that are actually existing. I am not drawn in this diagram out over here. These connections have not been drawn out at this place only because of some ease in problem modeling, ease in drawing. As they are parallel connection with some weights out here into the neural network architecture that we have. In the kind of neural network architecture that we have, these are the connections. So now all I have got simple is that my O3, the output O3 for any neuron J, and equivalently say for any output, any rule J is equal to summation of AI, those are the weights out over here. I, those are these inputs out here. I value from 1 to n plus a bias term and plus multiplied by the previous membership degree, which was nothing but O2 for the output J. These are the membership degrees that travel. So this is exactly the output that is gets, and we know what does it physically represent. We exactly know what does it physically represent. It is the implication operator with mapping from the inputs to the outputs. So from the input domain we went across into the output domain. From the antecedent part of the rules we worked over with the consequent part of the rule, where we got some kind of output with us. Now whenever we'll be dealing with the term output. So we've got the kind of output. We've done implication. We've got output. We have done some kind of implication. The next thing to happen are aggregation and defuzzification. The next thing to carry forward is aggregation and defuzzification in this type of system. In exactly this kind of system where we had modeled the output as nothing but a collection of, and we had modeled the output as a linear addition of all the previous inputs. That is how we were trying to model out our system, and hence in this system what would happen out is that my aggregation is simply a summation. My aggregation is simply a summation. And again there are no membership degrees involved, so I need not perform defuzzification over here. I need not perform any defuzzification. I am dealing in the output domain with no membership values now. I have got that the discrete outputs, each one of these. So I need to do only as per my fuzzy modeling scenario, as per my fuzzy modeling, as per whatever I have learnt in the fuzzy inference system, I now need to do only a summation of all the various outputs. That is the application of the aggregation operator. So my output O, all it does is that summation of O3J. J of course varying from 1 to all the roots M out over here. J varies from 1 to all the outputs over here, and that is where I get my final output O. So with this, something that we have done is that we know that what is drawn out over here as this lovely diagram, as this lovely figure. By sight we can say it's a neural network. It has connections, it has activation functions, it has summation, it has all those things that the neural network does. So by the very sight we can say that this is nothing but a neural network. It performs everything that the neural network does. It has the same architecture, it has all the principles that we study in neural network architecture and working. It has the same principles, so it's a neural network of course, but what it is doing is that it can by its very sight be converted into a fuzzy inference system. We know the underlying mathematics is a fuzzy inference system, so we added fuzzy modeling scenario over neural network. And of course, it's a well-working fuzzy inference system. You can convert it back into its another form where you will have all the membership degree followed by all the rules and everything. In the similar manner, you get the outputs as you normally get in a fuzzy inference system by the same calculations. So it's a fuzzy inference system, and what I have done is that I have added the learning capability of the neural network into these fuzzy inference systems. So the other task is also done, that I have added learning capability. And why do I say that I have added a learning capability? Give it a database of inputs, give it a database of targets, and run a simple back propagation algorithm over this. Your task is done. Give it the inputs, give it the targets, and simply run a back propagation algorithm. Your task would be all done. So what I would happen is that next time I do this kind of modeling, I make this kind of ANFIS architecture with the same working principles. All I am going to do is that I am going to take in a database containing the inputs and the targets, and I am going to simply say that perform a backpropagation algorithm. So for I equals to 1 to epochs, for every input and target in my database, what do? You simply find out what the output is. So I apply the input, I get my output. I say error equals to the input minus the target minus the output. I simply say this is what is the forward propagation. I simply say that you please layer by layer back propagate the error E for all the layers from ahead to backward. This will be from first layer to the fifth layer. This will be from the fifth layer to the first layer. So this will be the back propagation, and my BPA is done. So once I have already done that, I can simply work over with my backpropagation algorithm and train what my system is. I'll get in a very exciting system out over here. So next time you have a training database available, not necessary that you go in for a neural network. It's sometimes regarded as sometimes regarded as a conventional technique in soft computing that if you have a training database, you train it using the neural network. Not the case. You can benefit from the fuzzy modeling, the power of fuzzy modeling if you do not use a neural network but rather you use an ANFIS. And how to use an ANFIS? You generate an initial fuzzy system using there are a couple of mechanisms available that we will of course not study out in this lecture series. So you generate out some fuzzy inference system and you ask the backpropagation algorithm to learn the database. And after backpropagation algorithm does its task, what we get is the final fuzzy inference system that is optimal in terms of time, in terms of performance. Backpropagation algorithm in a 5-layer neural network with all those complex connections possible. It's quite a hefty task, it's quite time consuming in nature. It is very time consuming in nature because what we have is that we know inputs will be multiple. Inputs will be multiple. Each one of these inputs will be divided into a decent number of membership functions. Now even 3 membership function is large enough. Multiplied by the total number of inputs, you know the total number of membership function you need to handle. And of course I do not say that the membership function would be large because we know that the best fuzzy inference system taking the least number of membership function. So the total number of membership function no doubt would be quite large for all the inputs. The total number of rules also the same thing happens, that we say that the number of rules should be as less as possible. That's what we say. But in real life application, the mapping is complex, the mapping between the inputs and outputs, so the number of rules also may grow quite handsome in the number. And then of course you've got all those complex mathematics, so backpropagation algorithm becomes highly time consuming in nature. So what we ideally use, we use a hybrid learning algorithm. in place of a null propagation algorithm. And what we say is that there are two types of parameters. There are premise parameters and there are consequent parameters. We say that there are two parameters, one are the premise parameters and one are the consequent parameters. These what the BPA is supposed to carry forward. Tuning of parameters, what we call as the weights and biases in the neural network terminology. What are these weights and biases? The parameters of fuzzy inference system. So whenever I speak in the neural network domain, I use weights and biases. Whenever I speak in the fuzzy domain, I call them parameters. Similar to what we had studied in the fuzzy inference system and the evolutionary fuzzy system, all these are parameters that these learning algorithms they try to optimize. So because I am dealing with fuzzy domain, and having a look at it from the fuzzy domain, I am not saying they are weights and biases, these are the parameters. So the premise parameters are all those that happen before implication. These are the parameters that are become after implication operator. In a fuzzy sense, these are taken to be non-linear. These are the non-linear parameters, these are the linear parameters. They normally don't have an activation function. It's always some kind of summation or multiplication. It's always some kind of summation or some kind of multiplication involved. So these are the non-linear parameters. These are the linear parameters where it's normally the weighted addition over here. And these are non-linear parameters where we pass over some non-linear activation function. We carry forward the training in two steps. We keep the consequent parameters constant. We train them, and then we keep these constant and train them, and multiple cycles produce us the training result. So because we keep constant, these are lesser in number, they can be easily trained, and because these are kept constant, these are less in number, they can be trained. So in two steps, that's why the algorithm is called hybrid. That's why it's called as hybrid. In two steps, when repeated over epochs, when repeated over multiple epochs, we are able to get the task of training done. So for every epoch, we apply the first step, constant, learn, and then the reverse thing, constant, learn. These are kept constant, these are learned, these are kept constant, these are learned. And that is why the hybrid learning algorithm works. And of course, if I come up to a learning graph, that would be nothing but the standard where error is plotted with the parameter values. The error will keep reducing along with time. That is again, we saw how the BPA did that. BPA is exactly what we are looking at. BPA is exactly what the algorithm we are using. So the trends of the learning would be quite similar in nature. The trends, they can assume to be quite similar in nature. That's what we normally get when we actually train ANFIS. These are the trends that may be observed. So that was all about ANFIS. I'll take in a couple of moments to speak about the other hybrid systems that we would not be discussing about. We would not be discussing those systems as a part of the curriculum out over here. I'll just give it a brief out over here. The first one known as the fuzzy neural networks. I told you what was the inspiration behind the ANFIS. Again, we need to take the same two systems, the same two individual systems, the neural network and the fuzzy logic. The only thing that we do is that we take in a different motivation. Now it's the architecture, problem modeling, scenario, everything of the neural network. The same learning, everything of the neural network. We take up everything from the neural network. So these are ultimately neural networks, nothing else. These are completely neural networks, but we state that one of the limitations of the neural network is that they have crisp inputs, crisp mechanism of processing, crisp learning and crisp outputs. So it doesn't make a difference whether you would say step 1, step 2, step 3 in a normal rule based system, or you use a neural network which is nothing but a layer wise information processing. Everything is crisp. When we were going from normal production rules to a fuzzy domain, from normal rules we were going up and we were dealing with the fuzzy logic inspiration. We said that crispness is not good. Things need to be fuzzy. So why not add this fuzziness into the neural networks? So what do? We have the same neural network of inputs, some hidden layer neurons and some outputs over here. We have exactly the same architecture out over here, the input, the hidden layer, the outputs, multiple hidden layer if needed, but everything is fuzzy. We have fuzzy inputs, we've got fuzzy neurons, we've got fuzzy weights, and we've got fuzzy outputs. Everything is fuzzy. Why do I say everything is fuzzy? Because what I would say now, I will never give an input like 5 over here. I'll always say 5 with a membership degree of 0.1, 2 with a membership degree of 0.8, or whatever, x with a membership curve of mu x. That is what my inputs become. Not an x alone, x along with a membership degree. Again repeating what the fuzzy net arithmetic is. That's always input along with the membership degree. So these are the inputs. Similarly the weight, it's not a 0.1 weight, it's always a weight along with its membership degree. And the fuzzy neuron is of course a general domain. So that's the concept. Output is also fuzzy. It's always some output O along with some membership degree. So everything is fuzzy out over here. The only thing that I probably need to say is that because the neural network is same summation WI xi passing on the outputs, same training, same learning. Everything is the same. In these systems, everything is the same. But I'll have to make one transition. Earlier I was dealing with some arithmetic which was known as the crisp arithmetic. I was doing some W1 I1 plus W2 I2. I'll just need to perform the same W1 I1 plus W2 I2 but with fuzzy arithmetic. So only the change required is normal arithmetic to fuzzy arithmetic. And the only functions that you would require is the plus, the multiplication and the activation function. These are the only 3 arithmetic operations that neurons do. So I only require these 3 functions. Of course the learning part has to do with some gradient, some descent. We will not deal up with that, we will not deal up how learning is done. But for forward propagation, only for problem solving, these are the 3 functions required, where I need to know how do I do A plus B, A into B and F of A. It's a union operator. I say A plus B is nothing but A with a membership degree of mu A, B with a membership degree of mu B that I need to add. So there will be a number part of it and there will be a membership value part of it. Fuzzy numbers plus membership value. The number part of it is simply this A plus B and the membership degree of it is called as mu A plus B. And how do I get this membership value? I see for all combination for anything, I say that I want to be on the very safe side. Whatever maximum membership degree, whatever maximum uncertainty is possible, that is what I will give. So this is given by max of mu A plus mu B. It was a mu A over here, the same mu A here, and mu B over X over here. So for all combination A and B, for all combination of any kind of X, A and B, I find out what the maximum membership degree can be. Because again I need to calculate the maximum degree of uncertainty, so I have taken both of them and I calculate what is the maximum uncertainty. So if these are the 2 curves, let's say 0, 1 and 2, and let's say 1, 2 and 3, this is what is A, this is what is B. My A plus B is nothing but there will be an integral part of it and there will be a summation part, there will be a membership part of it. So this is what will be given by it was from 0 plus 1, 1, this is where it starts, 3 plus 2, 5, 5 is where it ends, and 2 plus 1, 3, this is where it has its peak. Exactly same thing follow for the multiplication part of it. So I will use up exactly the same equation. This will become A into B. Equation remaining the same. the graph would change. If these are the A and B, it will be 0 into 1, 0, 0 into 1, 0, 3 into 2, 6. And the curve being slightly like this, the mean happens to be something like this. So exactly the same thing, and exactly the same thing happens to be A, except for that now B is gone, and if B is gone, then I only have a mu A out over here, and if I have a mu A out over here, I draw its curve. The number part of it will be simply FA, the membership part of it will be mu A. I say if this is the equation, if this is what FA was, if this is what A was, this is what my FA would be, this is what the activation function is, this is what mu A is. So my membership degree would be given by point matching out over here. This is what the curve would translate into. This is what the activation function that I model, and this is what the transformation does. So these are what the fuzzy neural networks are, and that is how we apply them for problem solving, and that's how we will finish off the alpha today.